Good day everyone, welcome back to the channel. In this video, we are going to talk about how we can configure the environment. Earlier, as previously mentioned, the shell holds set of details known as environment throughout our session. Information stored in this space helps programs understand our setup. Although configuration files are typically used for program settings, some programs check the environment for specific values to modify their actions. With this knowledge, we can personalize our shell experience by leveraging the environment. In this chapter, we will work with the following commands. The first command we are going to look at is the printenv, print part or all of the environment, set shell options, export environment to subsequently executed programs, alias, create an alias for a command. Okay.
Unlock the world of Daisy Ninja puzzle books, where excitement meets brainpower. Dive into the mind-bending labyrinths of Maze Mastermind. Conquer the Sudoku challenges in Sudoku Ultimate. Uncover hidden words in Word Search Wizard. And decode mysteries in Word Spy Adventures. Whether you're soaring above the clouds or speeding down the tracks, turn your downtime into brain-boosting fun. Perfect for all ages, these books guarantee hours of entertainment. Daisy Ninja Puzzle Books, your passport to endless excitement on the go. New release each month.
Now, what is stored in the environment? In the environment, the shell holds two primary data types. Albeit with Bash, these types mostly appear similar. These types include environment variables and shell variables. Shell variables consist of data inserted by Bash, while environment variables encompass all other forms of data. Apart from variables, the shell also retains certain program-related information, specifically aliases and shell functions. We discussed aliases in chapter 5, while shell functions associated with shell scripting will be explored in part number 4. Okay. Examining the environment, we can check the environment contents using either the built-in set command in Bash or the printenv program. The set command reveals both shell and environment variables, while printenv specifically showcases the environment variable, as the environment content list can be quite extensive. It's advisable to channel the output of either command into less. So let's have a look. We'll say printenv and we'll pipe it to the less command. Now, to go through all the data that has been thrown at us, we can use the up and down arrow key. The reason is because we piped all the data through the less command. Now, what does this mean? Doing so, we should get something that looks like this, which it is. The displayed information comprises of a lineup of environment variables alongside the corresponding values. For instance, there's a variable named user with the value me. In our case, the user is dev. It can be found here. Additionally, the print environment command enables the listing of a particular variable's value. Okay, so once we get out of the less command, we can say print env and then we'll say user, and now it is going to print the value of the variable user. Okay, when invoked without any option or arguments, the set command showcases both the shell and environment variables along with any established shell functions. Unlike printenv, its output is thoughtfully arranged in alphabetical order. Okay, so let's say set, then we'll pipe it to the less command, and now you can see all the variables are arranged in alphabetical order. Okay, and now it's easy to find all the variables that we are looking. Okay, it is also possible to view the contents of a variable using the echo command like this. We can say, once we quit out of the less command, we can say echo, then the $, then the name of the variable, and now it is displaying the directory of the given user. Okay, one element of the environment that neither set nor printenv displays is the aliases. To see them, enter the alias command without arguments. So to do that, we can say alias, and these are all the aliases in the system. Okay, some interesting variables. The environment encompasses numerous variables, and while yours might not match the presented one here, you'll probably encounter the following variables within your own environment. So these are some of the variables that may be available in your system. Now let's quickly have a look what they are. First variable is the display variable, the name of your display. If you're running a graphical environment using this is :O, meaning the first display generated by the X server. Editor, the name of the program to be used for text editing. Shell, the name of your shell program. Home, the path name of your home directory. Lang defines the character set and collation order of your language. Old_pwd, the previous working directory. Pager, the name of the program to be used for paging output. This is often set to /user/bin/less. Path, separated list of directories that are searched when you enter the name of an executable program. PS1, prompt string 1. This defines the contents of your shell prompt, as we will later see. This can be extensively customized. PWD, the current working directory. Term, the name of your terminal type. Unix-like systems support many terminal protocols. This variable sets the protocol to be used with your terminal emulator. TZ or TZ specifies your time zone. Most Unix-like systems maintain the computer's internal clock in coordinated universal time, which is UTC, and then displays the local time by applying an offset specified by this variable. Username, that is your username. Okay, don't worry if some of these variables are missing. They vary by distribution. How is the environment established? Upon logging into the system, the bash program initiates and scans through a set of configuration scripts known as startup files. These files establish the default environment applicable to all users. Subsequently, additional startup files in our home directory delineate our individualized environment. The specific sequence varies based on the type of shell session initiated, which falls into two categories: a login shell session and a non-login shell session. Okay, a login shell session involves entering our username and password, such as when initiating a virtual console session. Conversely, a non-login shell session commonly happens when launching a terminal sessions within the graphical user interface, or GUI in short. Login shell read one or more startup files as shown. These are the files: /etc/profile. Content of the file is a global configuration script that applies to all users. Home directory, then .bash_profile, the user's personal startup file, can be used to extend or override settings in the global configuration script. And home directory .bash_login. If this directory is not found, bash attempts to read this script. Okay, then home directory .profile. If neither .bash profile nor the .bash login is found, bash attempts to read this file. This is the default in Debian-based distributions such as Ubuntu. Okay, non-login shell sessions read the following startup files. So /etc/bash.bashrc, a global configuration script that applies to all users, and .bashrc, a user's personal startup file, can be used to extend or override settings in the global configuration script. Apart from passing the mentioned startup files, non-login shells also acquire their environment from the parent process, typically originating from a login shell. Inspect your system to identify the available startup files from this list. Keep in mind that as most file names listed begin with the period, indicating they are hidden, you will need to utilize the ls-a option to view them. Okay, so when you say ls, it only shows all the visible directories and files, but when you say ls-a, it displays all the hidden files which start from the period. Okay, so it's .net, .pki, and so on, .nom. All these directories are hidden. You won't be able to see them in your file explorer unless you have enabled hidden files. Okay, for the everyday user, the .bash rc file holds significant importance as it's nearly always accessed. By default, non-login shell reads this file, and most login shells startup files are designed to also incorporate the reading of the .bash rc file. What is in a startup file, you might wonder? If we take a look inside a typical .bash profile taken from the CentOS 4 system, it looks something like this. So this is what a .bash profile file would look like, okay, in a CentOS system. Lines starting with the hash symbol are considered comments and are ignored by the shell, serving solely for human readability. The initial noteworthy content appears on the fourth line, showcasing the following code, which is if-f.bash rc, then .bash rc, which means if this file exists, then execute this file. Okay, this is called an if compound command, which we will cover fully when we get to the shell scripting in part 4. But for now, we will translate it like this. So if the file .bash rc exists, then read the file .bash rc, okay, which, as I said earlier. This piece of code illustrates how a login shell accesses the contents of .bash rc. The subsequent section in our startup file pertain to the path variable. Okay. Have you ever pondered how the shell locates commands when we input them on the command line? For instance, when we type ls, the shell doesn't scour the entire system to find the /bin/ls file or the command, the complete path name of the ls command. Okay. Instead, it scans through a compilation of directories listed within the path variable. The path variable is commonly, though not universally, contingent on the distribution established by the /etc/profile startup file, often utilizing this code, which is path equals to the path variable and the home variable /bin. Okay, the path is adjusted by appending the directory, which is home/bin at the list's conclusion. This showcases parameter expansion, a concept briefly discussed in chapter 7. To illustrate its functionality, give this a try. So we'll say foo equals, this is sum, then space, and then we'll close the quotes, then we'll say the $ foo. We'll have to write the echo command. Now it is going to print the foo variable that we created. Now we'll say foo equals $foo text, and then close the quotes. And now we'll say echo $foo. And now it says this is some text. So what has happened here? First, we declared a foo variable and we put this value inside it, a string. This is sum. Then we printed the foo variable using the echo command over here, and it printed out this text. This is sum. Then what we did, we created a foo variable. Then we put the value of the old foo variable in it, and then added this little string at the end of the value, which was already inside the old foo variable. So it was this is sum space. Then we added text, then the period after that. Okay. So then we printed the foo variable again using the echo command. We got this output. Okay. So using this technique, we can append text to the end of a variable's contents. Appending the string home variable /bin to the end of the path variable extends the list of directories inspected when a command is used. Consequently, when we aim to establish a directory within our home directory to house personal programs, the shell is set to assist us. Simply naming it bin will suffice, and we are all set to proceed. Note, many distributions provide this path setting by default. Some Debian-based distributions such as Ubuntu test for the existence of the home directory /bin directory at login and dynamically add it to the path variable if the directory is not found. Lastly, we have export path. The export command instructs the shell to share the contents of path with the child processes spawned from this shell. Now let's talk about modifying the environment. With an understanding of the location and content of starter files, we can edit them to tailor our environment to suit our preferences. Which files should we modify? As a guideline, if you aim to include directories in your path or define new environment variables, incorporate these modifications in .bash profile or its equivalent. As per your distribution, for instance, Ubuntu utilizes .profile. For other adjustments, use .bash rc unless you are the system administrator requiring alteration to the system-wide defaults. Confine your changes to files within your home directory. While it's feasible to modify files in /etc like profile, it's prudent to proceed cautiously for now. Okay, text editors. For modifying the shell's starter files and many other configuration files within the system, we rely on a tool known as a text editor. This program, akin to a word processor in certain aspects, enables editing text on screen using a movable cursor. Its distinction lies in supporting only plain text, excluding the formatting and other encompassing features tailored for programming tasks. Text editors serve as a primary tool for software developers to write code and aid system administrators in handling configuration files governing system operations. Linux hosts numerous text editors, likely with several installed on your system. Why the abundance? Primarily because programmers enjoy creating them, and given their extensive use by programmers, these editors are crafted to mirror their preferences and how they envision their functionality. Text editors are generally categorized as either graphical or text-based. Within GNOME or GNOME and KDE environments, you'll find various popular graphical editors. GNOME typically features an editor named gedit, commonly labeled as text editor in the GNOME menu. In KDE, you'll typically encounter 3 text editors: kedit, kwrite, and kate, varying in the complexity from simpler to more advanced. Okay, or you can install your own text editors such as Visual Studio Code. My personal preference is VS Code. Several text-based editors are available, with popular ones including Nano, V, often replaced with Vim, meaning V improved on most Linux systems, and Emacs. Nano, a user-friendly editor, was created as a substitute for the Pico editor within the Pine email suite. V, a traditional Unix-like system editor, will be the focus of our upcoming chapters. Emacs, initially developed by Richard Stallman, is a comprehensive multi-purpose programming environment. Although accessible, it's frequently included as a default installation on most Linux systems. Using a text editor. Every text editor can be accessed from the command line by inputting the editor's name followed by the file you wish to edit. If the file isn't present, the editor assumes you aim to create a new one. Here's an instance using gedit. So to do that, we will say gedit, then the name of the file. In this case, we'll name it some file, and now the editor is open. Okay. In our case, the gedit command opens the text editor, the default text editor installed in the system. All right. Executing this command will launch the gedit text editor, opening the file named some_file if it exists. Graphical text editors are typically intuitive, so we won't delve into them here. Instead, let's focus on our initial text-based editor, Nano. We'll launch Nano to edit the .bash rc file. However, before we proceed, let's practice safe computing. Whenever editing a crucial configuration file, it's wise to generate a backup copy as a precaution against accidental alterations. To create a backup of the bash rc file, follow these steps. Okay, let's close the editor. Now we'll say cp.bashrc to the .bashrc.bak. Okay, now it has made a backup of the .bashrc file. The name you give to the backup file is flexible. Choose something descriptive. Common extensions like .back, .save, .old, or .orig indicate backup files. Also keep in mind that CP will silently override existing files. Now that we have a backup file, we'll start the editor. So we'll say nano dot bash rc. Now this has opened the dot bash rc file within the nano editor. Once nano starts, we'll get a screen like this. As you can see, it looks pretty much same. All right. If your system does not have nano installed, you may use a graphical editor instead. Okay. The screen layout includes a top header, the file's text in the middle, and a command menu at the bottom in the nano editor. So this is the header where the version of the nano program is displayed and the name of the file. The content of the file is here, and then these are the commands. As it was created as a substitute for an email client editor, Nano has limited editing capabilities. In every text editor, the initial command to grasp is how to exit the program. In Nano, you exit by typing Ctrl X as indicated at the bottom menu with the notation #X, which means Ctrl plus X, denoting Ctrl X. This notion, employing the symbol like hat, represents control characters, widely used convention in various programs. All right. So to exit, you just say Ctrl plus X, and now you're back to your terminal. The next essential command is saving our work achieved in Nano by using the Ctrl O. Equipped with this information, we are set to start editing. Navigate to the end of the file using the down arrow key and or the page down key, then insert the following lines into the dot bash rc file. Okay, so let's start the editor again. Let's go at the bottom of the file. Now we'll say umask 3 zeros and 2 export hist control equals ignore dupes. Then we'll say export hist size equals 1000 alias l dot equals ls dash d dot star color equals auto, includes the quote single quotes, alias l equals ls dash l dash double dash color equals auto, and close the quotes. Okay, so your distribution may already include some of these lines, but duplicates won't hurt anything. Here is the meaning of our additions. So the line umask 0002 means set the umask to solve the problem with shared directory. As we discussed in chapter number 9, export hist control equals ignore dupes causes the shell's history recording features to ignore a command if the same command was just recorded. Export hist size equals 1000 increases the size of the command history from the default 500 lines to 1000 lines. Alias l dot equals ls dash d dot star dash dash color equals auto creates a new command called l, which displays all directory entries that begins with a dot. Now alias ll equals ls dash l dash dash color equals auto creates a new command called ll, which displays a long format directory listing. Several of our additions might not be immediately apparent, so it's advisable to include comments in our .bash rc files to provide explanation for humans. Using the editor, change our additions to look like this. Okay, now let's quickly add some comments. So we'll say change umask to make directory sharing easier. Okay, then we'll add extra line for readability. Then we'll say ignore duplicates in command history and increase history size to 1000 lines. Okay, and finally we'll say add some helpful aliases. All right, so we have now added an explanation for the code that we added to the .bash rc file. Okay, great. With our alterations finished, press Ctrl O to save the modified .bash rc file, then Ctrl X to exit Nano. Right, so we'll say Ctrl plus O, file name is now written, and then we'll say Ctrl X, and now we are back to the terminal. Why comments are important, you might wonder. When altering configuration files, it's wise to include comments to document your changes. While you might recall modifications made tomorrow, remembering them in 6 months might prove challenging. Adding comments is a favor to yourself in the future. Additionally, maintaining a log of changes can be beneficial. In shell scripts and bash startup files, comments typically start with the hash symbol. However, different configuration files may use alternate symbols. Most configuration files include comments serving as guidances. It's common to encounter lines in configuration files that are commented out to prevent them from impacting the associated program. This practice offers suggestions or demonstrates correct configuration syntax. For instance, in Ubuntu 8.0.4, a very old system.bash rc file, these lines are present. So some more ls aliases, ll equals ls-l, la equals ls-a, l equals to ls-cf. The last 3 lines comprise valid alias definitions but are currently commented out. Removing the leading hash symbol, a process known as uncommenting, would activate these aliases. Conversely, adding a hash symbol to the start of a line deactivates a configuration line while preserving its information. Okay, activating our changes. The modifications in our .bash rc won't be applied until we close our current terminal session and initiates a new one. This is because the .bash rc is read only at the session start. Yet we can compel bash to reread the updated bash rc file using the following command, which is source.bash rc. Now it's reactivated. After doing this, we should be able to see the effects of our changes. Try out one of the new aliases. So we created the ll alias, and now it is displaying the detailed information of the current working directory. All right, so this is how you can create aliases. Okay, so let's summarize the chapter. Throughout this chapter, we have acquired a crucial skill: editing configuration files using a text editor. As we explored command man page in the future, pay attention to the supported environment variables. There might be some valuable insights in the upcoming chapters. We'll delve into the shell functions and influential feature that can be integrated into bash startup files, further enhancing your assortment of customized commands. Alright guys, so do go through the chapter, do practice all the commands, do try them out, get a hang of them, and in the meantime have a good one, and I'll see you in the next video. Take care. Bye bye.